Hey folks, want to take some time here to kind of give a rehash of what we talked about in class as far as reviewing for the exam. Test is Tuesday, and I will try to get there early as I can, but probably can't get there before 15 till, but if you want to start at that time you can. And then we can run a little late, but not very, because we've got a class after hours. So I don't think it's going to be a long test in terms of writing stuff down. I think if you know what you're doing, you can get through it easily within an hour. But you've got that time if you need it in case you get stuck on something. Let's talk a little bit about what we're going to do on the test. So I'll call this Test 2 Review. Here we go. 3 sections. 3.1 is on divisibility. Okay, and we had problems on just general kind of divisibility, things like, make sure you know what it is. A divides B if there exists some integer n such that B is equal to an. You can look for a theorem or two. There's the chance of a problem or two where I just give you a general divisibility kind of thing, and you have to use the definition of divisibility to work it out. Problems that we worked like this, problems 2 through 6 in that section, and problem 17. We also in that section talked about the division algorithm, which kind of goes back to your old elementary school days when you didn't talk about decimal remainders. You didn't use decimals. You said you divided by something, and then you had a remainder of whatever. But the way we state that formally is for all a and b integers, and I think technically b. For all a, b, I think b needs to be a natural number. A integer, b, element natural number. There exists q and r that are integers, and again I think I want r to be a natural number, such that a equals bq plus r, and r falls between 0 and the b. The reason I'm throwing out the b and the r as integers, if you have integer over integer, you can always move a negative to the top, and then handle that with the quotient as well. So we certainly want r and b to be non-negative values. In the context we use this most of the time, we're talking about natural numbers anyway. But we worked some problems using this where we talked about, okay, here's what happens with the remainder. Problem 10 and 17 were like that in that section. We also in this section introduced relatively prime, which simply means A and B are my puppy's up here. He's doing okay. Are relatively prime if their greatest common divisor is just 1. And then in this section we didn't introduce this, but we did have some induction proofs on divisibility, problems 19 through 21. So on the test I could probably give you, like a general problem, and then maybe one involving the division algorithm. There'll be 2 or 3 problems out of this stuff, and then maybe like one induction proof or something. There'll be 2 to 3 problems out of 3.1 and 3.4. 3.4 is actually on divisibility tests, which they went through a bunch, and but they showed that the general way to prove these things is by using one of two theorems. In most cases, it was the sum theorem. Our sum theorem says this: suppose n divides a, then n divides a plus b if and only if n divides b. So we'd end up writing whatever number we're doing divisibility test for n. We'd end up taking our general kind of number and writing it like this, where we knew it n divides part of it, like 10 divides everything 10 and on, right? If you put that 0 there. And then that'll work if and only if n divides the other part right there. So we use that in a lot of those basic divisibility theorems. And then also the product theorem that we had, saying suppose m and n are relatively prime, then m times n divides a if and only if m divides a and n divides a. And that's how we got additional tests for things like 6. 2 and 3 are relatively prime. If 2 divides a number and 3 divides a number, then 6 would have to divide a number. Things like 22, for example, well, has to be divisible by 2 and 11. 15, 3 and 5. So you look for factors that are relatively prime and do the test for the two individuals. And let's see, so definitely know those two theorems, and also know the specific tests, because we may use them. I may say, here's this, like I remember they did something in the book, like here's a palindrome with an even number of digits, so it's always divisible by 11. We use these tests in problems 15 and 16. Product theorem we used in numbers 11 through 13, and sum theorem we used in problem 1 and problems 5 through 9. Okay. So 2 or 3 problems out of that divisibility section. And then we moved on to relations. Okay, and we talked about several properties. Reflexive property of that means that AA is in the relation. Oops, I'm sorry, I didn't mean to put. Is in the relation for all A in the set A. That's reflexive. Symmetric. If AB is in there, then BA is in there. That's symmetric. And transitive. If you've got AB in there and BC in there, then you got to have the shortcut A to C in there. That's what we mean by transitive. And then there was also a property antisymmetric. If AB is in there and then also BA is in there, then A and B have to be equal. Okay, that's what we mean by antisymmetric. We also had, we did all these kind of things in problems 5 through 7. So I could do that on the test. I could say, here's a relation, tell me does it have these properties? And there were some other things we looked at too. Other properties were like irreflexive properties. Sorry. So I could do something like that. I could throw you a curve and say, here's another property. I think the one I used in class was lopsided. if a relation has this property, it's lopsided. I don't know what that means. But, you know, and then say, okay, now tell me, is this a lopsided relation? You know, that kind of thing. We did stuff like that in problems 9 and 10. But the two biggies that we talked about that have stuck with us are composition of relations. It's 11 through 14, we did that. And then the inverse, problems 15 and 17, we did that. And those were properties that we've gone on to use throughout with equivalence relations, also when we get to 6.1, 6.2 with functions and inverse functions. So, but I could definitely throw you a relation, you know, squiggle means this, and you tell me if it has these properties, right? The other thing we did with relations is we talked about special relations called equivalence. These were relations that had certain properties. Specifically that they be, let me take them in order, reflexive. There is no order, but the order that I wrote them down previously. Symmetric and transitive. So after I ask about all those properties, I could then ask, well, is this an equivalence relation? You can tell me if it has those properties. And we did a lot of this. Problems 4 through 6, we did this in that section. And then also we can talk about the equivalence classes. And I could ask you, okay, here's an equivalence relation. What does the equivalence class of this element look like? And basically that's everything that's related to it, right, through the equivalence relation. And we did that in problem 4 and also I think in problem 6. Okay. And then the last two sections. So and then so probably 2 or 3 out of that 5.1, 5.2 area. And then we started talking about functions and certain properties. Of course, you need to know the definition of a function. Assigns, and it's in the book, but assigns exactly one value of the domain to the range. So it's a relation that assigns exactly one value to each, not really, I shouldn't say value, one element. Could be horses and pigs, right? It doesn't have to be numbers. One element to each element of the domain. But in particular here we talked about some special properties of functions being one-to-one. If f of a equals f of b, then a and b are equal. And that's we use that definition quite a bit in our theorems. If I ask you to prove that this function is one-to-one, I expect you to say, okay, well, let's suppose we've got two elements that are such that f of a is equal to f of b, and then you have to go through and show that they're equal. Okay. And then also onto, which just means there exists an a in the set, and I guess I'm talking about something a to b here in all my stuff. There exists an element a such that f of a equals b for all b in the codomain. Okay, in other words, the range equals the codomain. So there's a good chance I would put a function on there and say, is this function one-to-one? Is it onto? That kind of business. We also, let's see, and we did stuff like this in problems 3, 5, 6, 11 in particular mentioned onto 12, and 13 in particular mention 1-to-1. Okay. And then 6.2, we talked about inverse relations and inverse functions. Okay, and I think this is an important distinction. Always in algebra, if we use the notation F inverse, we meant that had that the inverse was a function. That's not the case here, right? We can talk about the inverse relation and still use that F inverse notation without it necessarily being a function. In fact, it's only a function. This is one of our theorems. Is a function if and only if F is both 1-to-1 and onto. The big thing here, we did some properties of, if we look at subsets of either our domain or codomain, and we go back and how does that function when it's applied to, say, a union or an intersection or a difference, how does that work itself out under the function? Can you separate those things into a union? Can you separate those things into a intersection or a difference? So we did a bunch of theorems like that, and I would probably throw something like that at you on the test as well. We did that in problems 9 through 14 and 6.2, which we worked yesterday, which I will work again for you here in just a few moments. I'm going to go through and work those problems, give you a nice clean version of them, and you'll have that to study by. Okay, so that's about it. So out of 6.1 and 6.2, then probably 2 or 3 problems as well. And I'm looking, probably about 8. Some of them will have pieces, like I'll say, here's a function. A, is this 1-to-1? B, is it onto? Something like that maybe. Or like with relation, A, is it reflexive? B, is it symmetric? C, is it transitive? Stuff like that. So there may be some parts, but probably 2 major problems per page is what I'm figuring. That seems to work its way out pretty good for you in terms of time and getting finished within an hour or so. And I think I can cover everything that we've talked about in that time, in that many questions. Okay, Tuesday. Oh, also on Tuesday I will take up the homework from 6.1 and 6.2. I didn't take them up on Thursday because I wanted you to have them in your hands. Plus we had just stopped working 6.2. But I didn't take up 6.1 even though we finished it, because I want you to have your homework in your hand as you study. So I'll see you Tuesday. Study hard. Let's do well on that test. I don't like grading bad tests. So don't give me a bad test. Give me a good test. All right. See you then.